So this video is for Chem 2000. It's inside the organic chemistry unit. It's an introduction to the topic of isomers for the spring 2016, primarily for my class, but if you're in Michael's class, that's totally fine that you can use this, but he will go through this with you. So this is sort of a flipped classroom type idea for my students where I'm going to ask them to look at this video prior to class, and then we'll go through more examples in class. So I'm expecting you to have watched this beforehand, but Michael's class, just ignore that. So the other reason I'm doing this is because I feel like this topic is a bit confusing without the visual aids, and molecule kits tend to help with that. So there's lots of different types of models that I'm going to make with my model kit and just explain to you the different types of structural versus stereoisomers for Chem 2000. So this is my model kit. If you're not moving on to Chem 2500 or 2600, you don't have to buy a model kit, but these are the ones that are for sale here. This one's from the bookstore. It's pricey, it's $80, but it's really nice. It'll do everything, lots of colors, some lone pairs in there. So that's one of your options. That's the one I'll use for this video. The other option is this kit here, Molecular Visions. So you open up, it's a bit different. The pieces snap together, so you can see that it looks different. This is the kit I'll bring to class. And these kits are only $30. They're on sale from Greg Patnotes, so I'm going to show you his mugshot and his office number and his email. So if you want to buy one of those kits, completely optional for Chem 2000, but if you need it if you're going into 2500 or 2600, you need it. And if you want to use a model kit but you don't want to actually spend money, the other option is to take some olives, go to the bar with your buddies. Here's some Q-tips, or not Q-tips, toothpicks, and you can just, here's a little cameo from our dino friend, make your own model kit. Okay, now within this topic of isomers, there are several different types. So the first question you need to ask yourself is, how do I identify the different types of isomers? And your textbook has actually handled this quite nicely by creating a flow chart. So I'm going to use that chart in my discussion and we'll work our way through it. Not to worry if you don't have the textbook, I've attached a copy of that chart to our main webpage. So if you scroll down to the bottom, you'll see it. It's a link that's called Identifying Isomers. Just click on that link and it will open up, and it's just right there. So the definition of an isomer is a molecule with the same molecular formula as another molecule, but with a different chemical structure. So you're looking at two compounds and asking this question, do they have the same molecular formula? Once the answer is yes, and you're in that very broad isomeric definition, you can split it into two main types. And so the question you have to ask before you can do that is, do they have the same connectivity between the atoms? And if the answer is no, then those are structural isomers. And so we're going to go there first. If the connectivity is the same, that's stereoisomers, so we'll do that last. But within structural, or what the textbook calls constitutional, there are three main types: skeletal, positional, and functional. So I'm going to build some molecules and we'll look at those different types. Okay, so I'm going to demonstrate skeletal type structural isomers just using a 5-carbon hydrocarbon chain. So just pretend that the hydrogens are attached. These two are the exact same chemical structure and molecular formula. So in order to make structural isomers, I have to alter this somehow. So what I want to do is try things like taking off at 1 carbon and putting it somewhere in the chain and see, is that now different from this one? And if it is, then they're structural isomers. So these would be considered structural isomers. Now I took 1 off. If I take 2 off, so go this and then put this somewhere, is it actually different from the isomer I just showed you? And it turns out, no, it's not. It's actually the same. So play with them when you're drawing them, look at them from different angles, or or you look at your drawing and say, is it different? And if it's not, then it's not a structural isomer. So a third type structural isomer would be this one. You cannot do this, though. You couldn't take this and make a 5-carbon ring, because then you only have in this would be C5H10, because there would only be 2 hydrogens. So that doesn't count. It has to be the exact same, and by forming the ring, you lose that same molecular formula. So these are a few of the structures you can make that are different. For positional type structural isomers, we need to add a functional group, a different type of atom, because you can't show it, you can't have that kind with just carbon. So I'm going to use oxygen and pretend that this is an OH group. And depending on where, so you have the same, you have both of these being an alcohol, but depending on where you, I can't see the whole, where you put that oxygen. So it's still an alcohol, it's still an OH group, but it's at a different point in the ring. Those are called positional isomers. So if you put it there, it's different from that one. If you put it on the middle one, but it's still a positional, it's still an alcohol, so it's still a positional isomer. Functional type structural isomers are when the functional group changes. So both of these right now are still alcohols, they're still OH groups. But if I was to take off that oxygen and actually put it along the chain so that it's now attached to carbons on both ends, now we have an ether, and so the functional group has changed. So that's what you're looking for within the broader category of structural isomers. Functional groups are changing. Okay, so now that we've dealt with structural isomers, we need to deal with when our compounds have the exact same connectivity. And that's this deeper branch called stereoisomers, and it can get a little tricky inside this one. Now, I'm not going to spend a lot of time with this first question that they ask, which is, can the compounds be interconverted by rotation about a single bond? When the answer to that is yes, those are called conformational or conformers or rotational isomers, etc. And so I'm going to show you what that looks like. I've built a couple of molecules here. And so what we're talking about is rotation about this single bond here between these 2 carbons. And so right now they're the exact same molecule, but if I was to rotate this one by 120 degrees, now these 2 molecules are slightly different. They would have slightly different energies, and you can only consider them to be stereoisomers if you can isolate them from one another. So think low temperature, that sort of scenario. If you can do that, if you can isolate them from each other, those are conformational stereoisomers. Okay, so if the answer is no to the rotation, then you have to actually physically break a bond in order to interconvert the 2 compounds. And that's where the majority of the stereoisomers that you're going to see are going to lie in is this no category. And so it gets split into subcategories, but the main group is called configurational, okay? And then below that there are some subcategories, and these are names you're going to need to know. So the first question under configurational, there's actually 2 branches here that end up at the same place. One is saying, are the compounds cyclic? I'm going to show you some cyclic compounds that actually end up as enantiomers, but for now let's deal with geometric. Is the isomerism at a double bond? So you're looking for double bonds and you're looking for rings. If the answer to that is yes, you're in the geometric category. So those look like this. So what I've done is just built some simple double bonded carbon molecules here that have a cis and a trans conformation. So this one has your trans conformation versus a cis. So pretend they're like chlorines or something attached to these carbons. And if you look at them, they have the exact same connectivity, but you cannot interconvert them because you cannot rotate about that double bond. Alternatively, you can look at rings and see cis and trans conformations. So here's a cis conformation, which is clearly different from the trans, and so these would be considered to be geometric type isomers, cis versus ice. So you see them in rings and double bonds. Okay, so now if the isomerism is not at the double bond, so that's what's going to break up the last group of stereoisomers. If the answer to that is no, then you ask, are they mirror images of one another? And if the answer is yes, then you're in enantiomers. And so we need to talk about something called chirality when we talk about enantiomers. And your hands are chirals, so they are non-superimposable mirror images of each other. So what I've done is built two molecules that are mirror images of each other. If you took a mirror plane and put it between them, they are mirror images. But if you then try to superimpose this one on itself, you can get two of the groups to line up, but not the other two. And so no matter how you rotate that, you're not going to see them being able to be superimposed on each other. So that's the broader category of enantiomers. I'm going to show you some more examples. So when we're talking about chirality, the criteria for having a chiral molecule is you need to have at least one stereogenic center. And so what you're looking for is a carbon that has four groups that are different. So that molecule before had four different groups around it. But what happens when you're in a ring? Okay, so these are not geometric isomers, but there are carbons here. There are 5 carbons here, and you need to look at them. So these ones that just have 2 hydrogens around them, clearly they are not going to count. They do not have stereocenters. But this one has a hydrogen, and then it has an oxygen, and then it has 2 carbons. And those carbons have the same atoms around them. So how do we decide if this is a stereocenter? Well, we need to work our way around the ring. So what you need to do is kind of position it and then move your way to the next atom on each side of the ring and say, are those the same? And if the answer is yes, then you need to keep moving to the next one. Now I've moved to this one, and this carbon has 2 hydrogens, but this carbon has a different atom. So the next carbons are not the same. So that means that this is a stereocenter. If this was a hydrogen, and so that these two were the same, then that would mean that this is not a stereocenter, because these two atoms, these two environments are the exact same, and you need to have all 4 be different. Here's another example of when you're looking for an enantiomer. So you want to start here, so it's another ring. Start here at this carbon, so it's got these 2 groups are different, but then you work your way around the ring again. So you start at these 2 carbons and then move your way to these 2 carbons. Those 2 are the same, those 2 are the same, and then you hit here, and even though there's a different group here, they both hit it at the same time. So this is actually the same, and so this is not a stereoisomer because the environment on this side is the exact same as the environment on this side. And if you tried to build an enantiomer, you would see that it is in fact superimposable on itself. Okay, so now we're in the final category where we're asking the question, again, are the compounds mirror images of each other? If the answer is no, then those are called diastereomers. Okay, so let's look at an example of that. These are actually still enantiomers, so I've built a 5-carbon chain. But if you see, if you look along the carbon atoms, this 3rd carbon is a chiral center, a stereocenter, because it has 1, 2, and then this is different than this because of this right here. So that would be a chiral center. This would be a chiral center because that group is different than this group here, and then these 2 are different. So you're looking for 4 different groups around the carbons. Okay, so these are the enantiomers of each other. If I want to see a diastereomer, remember these are mirror images, but they're non-superimposable. If I want to make a diastereomer, I'm just going to change 2 atoms here. So I'm just switching the hydrogen with the oxygen, and I'll put that back down. And voila, what do we see? These are no longer superimposable mirror images. The connectivity is still the same. You still have 3 hydrogens on the last carbons, and those 2 oxygens are still coming off those 2nd and 3rd carbons there. but they are no longer mirror images of each other.